Welcome to Tech Girl Kannada YouTube channel.
Modern communication system scheme. Information source, information input, transducers, message, and then baseband message signal transmitter, transmitted signal to channel, noise, a received signal, receiver, recovered baseband message signal, output transducer, final destination, it is original message. This is the schematic block diagram of a basic communication system in most general form. The communication engineering means electrical communication. The electrical communication is a process by which the information or message is transmitted from one point to another, from one person to another, or from place to another in the form of electrical signals through some communication links. The basic communication system provides a link between the information source and its destination. The process of electrical communication involves sending, receiving, and processing information in electrical form. A basic communication system consists of certain units called constituent subsystems or stages. We may also note that the information to be transmitted passes through a number of stages of the communication system prior it reaches its destination. The main constituents of the basic communication systems are information source and input, transducer, transmitter, channel, noise. Explain the following with respect to communication system. Information source, transducers, analog signals, digital signals, receiver, output transducer, and final destination. There are many types of communication systems. Example, analog, digital, radio, line communication systems. Information source and input transducers. A communication system transmits information from an information source to the destination. Hence, the first stage of the communication system is the information source. The physical form of the information is represented by a message that is originated by an information source, that is, example, a sentence or paragraph spoken by a person is a message that contains some information. The person in this case acts as information source. Few of the familiar examples of messages are voice, live scenes, music, written text, and emails. Definition: transducer. A transducer is a device that converts a non-electrical energy into its corresponding electrical energy called signal, and vice versa. Example, during a telephone conversation, the words spoken by a person are in the form of source energy, sound energy. This has to be converted into the equivalent electrical form prior it is transmitted. An example of transducer is a microphone. Microphone converts sound signals into the corresponding electrical signals. Similarly, a television picture tube converts electrical signals into its corresponding pictures. Some other examples of transducers are movie cameras, video cassette recorder, VCR heads, tape recorder heads, and loudspeakers. There are two types of signals: analog signal, digital signal. Analog signal, function value A, analog signal, digital, pure sine wave. It is analog signals are pure sine wave. Time, function value, time. Typical speech signal will be like this. Typical speech signal. An analog signal is a function of time and has a continuous range of values. However, there is a definite function value of the analog signal at each point of time. A familiar example of analog signal or analog waveform is a pure sine wave. A practical example of an analog signal is voice signal. When a voice signal is converted into electrical form by the microphone, one gets a corresponding electrical analog signal. Digital signal time, function value time T1, T2, T3, T4, T5. Digital signal. The digital signal does not have continuous function values on a time scale. It is discrete in nature, that is, it has some values at discrete timings in between two consecutive values. The signal values is either 0 or different value. Familiar example of a digital signal is the sound signal produced by drum beats. Digital signals in their true sense corresponding to a binary digital signal where the discrete amplitude of the signal is coded into binary digits represented by 0 and 1. The analog signal, which is continuous in time, is converted to discrete time using a procedure calling sampling. The continuous amplitude of the analog signal is converted into discrete amplitude using the process called quantization. Procedure is sampling, process is quantization. Sampling and quantization are together termed as analog to digital converter, that is ADC, and the circuitry that performs this operation is called analog to digital converter. Transmitter. Explain the block diagram of typical transmitter. Baseband. Baseband time. Low, high. T1, T2, T1, T2, T1, T2. Processed baseband signal. Same thing. F1, F2, F1, F2, F1, F2. Time. Frequency representing low, frequency representing high. Representing low, high. The processing of the baseband signal. The baseband signal, which is the output of an input transducer, is the input to the transmitter. This baseband signal S of t is suitable for transmission in the form in which it is generated by the transducer. The transmitter section processes the signal prior transmission. Baseband signal S of t is this: modulated carrier state C of t, modulated stage, modulated signal X of t, voltage amplifier stages, power amplifier stages X of t, TO. Those are the amplifier stages. Then it is taken as transmitter channel. Block diagram representing schematic of an analog transmitter section. There are two following options for processing signals prior transmission. The baseband signal, which lies in the low frequency spectrum, is translated to a higher frequency spectrum. The baseband signal is transmitted without translating it to a higher frequency spectrum. We call the communication system as a carrier communication system. In this system, the baseband signal is carried by the higher frequency signal called the carrier signal. In the later case, we call the system as the baseband communication system. Because the baseband signal is transmitted without translating it to a higher frequency spectrum. The carrier communication system is based on the principle of translating a low frequency baseband signal to higher frequency spectrum. This process is termed as modulation. Now, as the baseband signal is the digital signal, the carrier communication system is called the digital communication system. If the baseband signal is an analog signal, the carrier communication system is called as an analog communication system. And for processing analog communication system, analog modulation techniques are used. 1.5. Since the baseband signal S of t applied to the modulated stage, this stage translated the baseband signal from the low frequency spectrum to high frequency spectrum. This stage also receives another input called the carrier signal C of t, which is generated by a high frequency carrier oscillator. Modulation takes place at this stage with the baseband and the carrier signals. As two inputs after modulation, the baseband's signal is translated to a higher frequency spectrum and the carrier signal is said to be modulated by the baseband signals. The output of the modulated stage is called the modulated signal and the is designated as x of t. The voltage of the modulated signal is then amplified to drive the last stage of the transmitter called the power amplifier stage. This stage amplifies the power of the modulated signal and thus it carries enough power to reach the receiver stage of the communication system. Finally, the signal is passed to the transmission medium or channel. Differentiate between hardware and software channels. Channel or medium. Provide example for each. The transmitter medium between the transmission medium between the transmitter and the receiver is called the channel. Depending on the physical implementations, one can classify the channels in the following two groups. Hardware channels. These channels are man-made structure which can be used as transmission medium. There are following three possible implementations of the hardware channels. Transmission lines, waveguides, optical fiber cables. Transmission lines. This example of transmission lines are twisted pair cables used in landline telephony and coaxial cables used for cable TV. Transmission disadvantage. Transmission lines are not suitable for ultra high frequency transmission. To transmit the signals at ultra high frequency range, waveguides are employed as medium. Waveguides. Waveguides are hollow, circular or rectangular metallic structure. The signals enter the waveguide are reflected at the metallic walls and propagate towards the other end of the waveguide. Optical fiber cables. Optical fiber cables are highly sophisticated transmission media in the form of extremely thin circular pipes. Signals are transmitted in the form of light energy in optical fiber cables. In general, there is always a physical link between the transmitter and the receiver in hardware channels. A communication system that makes use of hardware channel is called as line communication system. Example, landline telephony and cable TV network. Software channels, there are certain natural resources which can be used as a transmission medium for signals. Such transmission media is called software channels. The possible nature resources that can be used as software channels are air or open space and seawater. The most widely used software channel is air or open space. The signals are transmitted in the form of electromagnetic waves, also called as radio waves. The radio waves travels to open source at the speed equal to the light of equal to that of c is equals to 3 into 10 power 8 meters per second. Systems that use radio waves to transmit signals through open space are called radio communication system. Example, radio broadcast, television transmission, satellite communication, and cellular mobile communication. Define noise. Describe the different types of external noise and internal noise in communication system. Noise is defined as the unwanted electrical energy of random and unpredictable nature present in the system due to any cause. Noise is defined as the unwanted electrical energy of random and unpredictable nature present in the system due to any cause. Noise is an electrical disturbance which does not contain any useful information. The noise introduced by the transmission medium is called extraneous External noise, extraneous or external noise. The main cause of internal noise is the thermal agitation of atoms and electrons. The noise introduced by the transmission medium is called extraneous or external noise. The main cause of the internal noise is thermal agitation of atoms and electrons of the electronic components used in equipment. External noise is introduced by the transmission medium. External noise is so called because the transmission between is external medium is external to the receiver. One can divide the external noise into the following three groups. Atmospheric or static noise. The main source of noises are lightning discharges and natural electrical disturbances in atmosphere. These electrical disturbances are received by the receiving antenna and are mixed with the signal as noise. Atmospheric noise is in the form of impulses that are random in nature. Atmospheric noise has a wide range of frequency components and is practiced spread over the entire frequency spectrum. Man-made industrial noise. Main source of the noise are automobile, aircraft ignition, electric motors, heavy electrical machines, switching gears, leakage from high voltage electrical supply lines, and fluorescent lights. These noises heavier in industrial areas than in non-industrial areas, and this is why it is called industrial noise. This type of noise spans a frequency of 700 megahertz. The amount of noise received increases with the increase in the bandwidth of the receiver. This is why the transmission equipment be installed away from the industrial areas. Extraterrestrial or space noise. Outer space is also a source of external noise that comes from sun and stars. This noise is of two types: solar noise, cosmic noise. Solar noise. The source of solar noise is the sun, which continuously emits electrical energy consisting of frequencies that lie within a very large frequency spectrum. These frequencies are covered the radio frequency that is used for communication systems. Cosmic noise. The source of cosmic noise is also stars, which also radiate electrical energy over a wide range frequency covering the radio frequency spectrum. Galaxies are also the source of space noises. The noise from galaxies is very strong but weakens as it reaches the earth due to the distances. Internal noise. The noise introduced within the receiver is known as internal noise. The noise can be generated into thermal Johnson's noise, white noise, short or transistor noise, thermal or Johnson's or white noise. This noise is generated with resistors used in the circuit. This noise appears due to the random motion of electrons and molecules inside the resistor. The resistor part of the complex impedance in a circuit is also a source of thermal noise. Due to the thermal energy, the electrons and atoms and molecules within the resistors agitate and generate random electrical signals, which is noise. The maximum output noise power Pn of the resistor is given as Pn is equals to kdB, where K is equals to 1.38 into 10 power minus 23 joule per Kelvin as Boltzmann constant. T is absolute temperature, V is bandwidth in Hertz. Short or transistor noise. This noise is generated inside a transistor used in an amplifier. Short noise is not only generated in an amplifier, it is also present in active devices, example bipolar junction transistors. Short noises appears because of the random movement of electrons and holes inside the transistor and the presence of random electrons or at the output terminal of the transistor in amplifiers. Short noise is similar to thermal noise in that its spectrum is flat, except in the high microwave frequency range. The expression for short noise shows that it is directly proportional to the output current and inversely proportional to the transconductance of the transistor. Define SNR and noise figure F. Explain the relationship between them. SNR and noise figure F. One can define the SNR as the ratio of the signal power to the noise power at a point in circuit. We may note that SNR is the measure of the signal power relative to the noise power at a particular point in the circuit. Now, if PS is the signal power and PN is noise power, SNR is expressed as S by N. It is given as S by N is equals to PS by PN. PS is equals to Vs square R and Pn is equals to Vn square R. Then S by R is equals to PS by Pn is equals to Vs square by R by Vn square R, where Vs is signal voltage and Vn is noise voltage. In addition, it is assumed that both the signal and noise powers are dissipated in the same resistor. Therefore, SNR can be expressed in terms of decibels, dB, as S by N of dB is equals to 10 log 10 Vs square by Vn square. S by N of dB is equals to 20 log 10 log base 10 Vs by Vn. For example, if a particular point in the circuit, the signal and noise voltages are given as 3.5 mV and 0.75 mV respectively, SNR in dB is calculated as S by N dB is equals to 20 log base 10 3.5 by 0.75. That is 20 log base 10 of 4.66. Then SNR is equal to 13.38 dB. Clearly, the SNR of the circuit at the point is 13.38 decibel. The noise figure F is a measure of noise introduced by the circuit. It is defined as the ratio of the signal to noise power at the input of the circuit and the signal to noise power at the output of the circuit. Noise figure F can be expressed as F is equals to S by N power at the input terminals of the circuit by S by N power at the output terminals of the circuit. We can see that if F is unity, the noise power introduced by the circuit is 0, as both the input and output S by N powers are the same. Write a short notes on noise measurement techniques. Noise measurement technique. The noise figure F is the measure of the noise performance of a device such as an amplifier or a receiver. The device whose noise figure is measured is known as the device under test, DUT. The noise figure of DUT is measured using a diode noise generator. When a DC voltage is applied across the diode, this generator produces short noise. The DUC is connected at the output. The DUT is connected at the output terminals of the diode noise generator. Figure 1.6 shows the circuit arrangement of the measurement of the noise figure of DUT using the diode noise generator. Device under test. Diode noise generator, PN, then RI, ROR out, then VN out. Device under test. Circuit for the measurement of noise figure of the DUT. In the figure 1.6, VNI denotes the output noise voltage of the diode noise generator, which is in the input noise voltage for the DUT. RI and RO are the respectively in the input impedance and output impedance of the DUT. The voltage developed across RO, marked as VNO, is the output voltage of the DUT. For measuring the noise figure F of the DUT, Using the circuit shown in the figure 1.6, one will have to perform the following steps. The input DC voltage of the diode generator is switched off. Now diode current is 0 under this condition. The output hour of the DUT is measured with 0 diode current condition. Input DC supply of the diode noise generator is switched on. The supply is variable and can be adjusted to any value. The input DC supply of the diode noise generator is increased until the output power of the DUT becomes double the output power under 0 diode current condition obtained in the step 2. Now the diode noise generator current under the condition started in step 4 is measured and designated as ID. The noise figure can be estimated using the following relation: F is equals to 19.3 RI/IO, where RI is in ohms and ID is in amperes. Explain the detailed block diagram of typical receiver. The task of the receiver is to provide the original information to the user. This information is altered due to the process of the transmitter side. The signal received by the receiver thus does not contain information in its original form. The receiver system receives the transmitted signal and performs some processing on it to recover the original baseband signal. A receiver signal R of T, front-end voltage amplifier R of T, demodulator S dash of T, recovered baseband signal, voltage amplifier, power amplifier, amplifier stage S dash of T to final destination. Detailed block diagram of a typical receiver section. From figure 1.7, it is evident that the receiver signal R of T is first amplified by the front-end voltage amplifier. This is done to strengthen the received signal, which is weak, and to facilitate easy processing. Next, the signal is given to the demodulator, which in turn demodulates the received signal to recover the original baseband signal. Interestingly, the type of demodulation is based on the type of modulation employed at the transmitter. After recovering the original baseband signal, its voltage and power is amplified prior to final destination block. Final destination. Explain the detailed block diagram exhibiting the final destination. Final destination is the last block of communication change. The destination is the user that receives the information and interprets it for useful purposes. The user can either be a human being or a machine that can make certain decisions based on the information received. Example: if a message is transmitted in the form of spoken words, then the user can be a human being who makes certain decision on its reception. A live telecast of a football match is meant for a human being as a user. In some cases, one can use a computer for the interpretation of the received information and takes appropriate action based on the information. The destination block converts the baseband signal, which contains information in electrical form, back into its original non-electrical form, to be delivered to the user. The constituents of the destination block are on an output transducer, which converts the baseband signal from its electrical form to its original non-electrical form, and the user. However, the output transducer works opposite to the input transducer. S dash of T, recovered message signal, output transducer, message, the user, destination. Detailed block diagram exhibiting the final destination. Now, if the transmitter transmits a voice signal, then the output transducer is a loudspeaker. Interestingly, this function is reversed in microphone. The speaker delivers the message in the form of sound energy, which contains some information to the human being who is user for this information. The user interprets this information and accordingly takes appropriate decisions. This completes the entire communication process. Figure 1.9 shows the detailed diagram of the complete communication change of basic communication system. This diagram includes all the blocks with their detailed process. Here is the diagram. Information system, message, information source, message, input transducer, then we have carrier, oscillator, baseband signal, modulated stage, that is S of t, should be modulated signal, X of t, then voltage amplifier, power amplifier, amplifier stage, transmitter, then the channel and the noise. X of t. That can be taken as here R of t, received signal, front end voltage amplifier, R of t, R of t, received signal, front end amplifier, R of t, demodulator, then S dash of t, voltage amplifier, power amplifier, amplifier stage, S dash of t, output transducer, the user, the message, destination, the receiver. This is the detailed schematic block diagram of the basic communication system. Explain the detailed schematic diagram of the basic communication system. Distinguish between amplitude modulation AM and frequency modulation FM. Amplitude modulation, frequency modulation. Amplitude of carrier is varied in accordance with amplitude of modulating signal, keeping frequency and phase constant. Frequency of carrier is varied in accordance with the amplitude of frequency of the modulating signal, keeping amplitude and phase as constant. Constant parameters are frequency and phase. Constant parameters are amplitude and phase. Modulating signal, it is in fish symbol. Modulated signal, it is an uneven signal. AC plus AM, AM wave, AC plus AC minus AC, FM wave. Modulation index MA is equals to AM by AC. Modulation index MF is equals to delta W by WM. AM is equals to peak value of the amplitude of the modulating signal, peak value of the amplitude of the carrier signal. Delta W, frequency deviation, WM, frequency of the modulating signal. Number of sidebands in AM are only 2. Number of sidebands are infinite and depends on MF. Bandwidth required is BW is equals to 2FM. Bandwidth required is BW is equals to 2 into delta W plus WM. Can transmit long distance, short distance. AM equivalent equipment are less complex. FM transmission and reception equipment are more complex. AM receivers are not immune to noise. FM receivers are immune to noise. Application video transmission in TV, AM radio broadcasting. Application broadcasting FM audio transmission in TV. Define amplitude modulation. Explain the amplitude modulation with relevant expressions and waveforms. Amplitude modulation. Amplitude modulation is defined as a modulation technique in which the instantaneous amplitude of the carrier signal is varied in accordance with the instantaneous amplitude of the analog modulating signal to be transmitted. The modulating signal is the analog baseband signal, which is random and has low frequency, while the carrier signal is always a sinusoidal wave with high frequency. The variation in the amplitude of the carrier signal represents the information carried. 2.1 shows the high frequency carrier signal, modulating signal and modulating signal. It can be seen from the figure that the amplitude of the carrier signal varies in accordance with the modulating signal, while the frequency and phase of the carrier signal remain unchanged. It can be clearly seen from this figure 2.1 that the modulating signal seems to be superimposed on the carrier signal. The amplitude variations in the peak values of the carrier signal exactly replicates the modulating signal at different points in time, which is known as an envelope. High frequency modulating signal. Modulated signal. Waveforms related to amplitude modulation. Equation of AM wave. Modulating signal is taken as the pure sinusoidal wave as given by the equation xt am cos wmt plus t plus theta m, where the carrier signal, which is always a high frequency wave, given as c of t ac cos wct plus t theta c. The parameters used in the equation 1 and 2 represents xt is instantaneous amplitude of the modulation signal. Ct instantaneous amplitude of the carrier signal. Am peak value of the amplitude of the modulating signal. AC peak value of the amplitude of the carrier signal. Wm angular frequency of the modulating signal. Wc angular frequency of the carrier signal. Theta m initial phase of the model signal. Theta c initial phase of the carrier signal. Ignore frequency and phase in equation 1 and 2. We get xt is am cos omega mt, ct is equals to ac cos wct. The modulated carrier signal can be represented mathematically by the following equation, that is s of t a cos omega ct is directly proportional to ac plus x of t, where a is peak amplitude of the modulated signal. Modulation index in AM wave. In equation 6, if we consider the proportionality constant equal to 1, then we have A is equals to AC plus x of t, 7. Substituting equation 3 in equation 7, we get A is equals to AC plus AM cos omega mt. A is equals to AC plus AC into 1 plus AM by AC cos omega t. That is MA is equals to AM by AC. MA is the modulation index of an AM wave. So we can modify equation 9 as to A is equals to AC into 1 plus MA cos omega mt. From equation 10, definition of modulation index. It is defined as the ratio of the amplitude of the modulating signal and the carrier signal. Depending on the value of the modulator index, modulation can be classified as follows. When MA is equals to 1, AM is equals to AC, called 100% modulation. When MA is less than 1, AM is less than AC, called under modulation. When MA is greater than 1, AM is greater than AC, then it is called over modulation. Frequency spectrum and bandwidth of AM wave. If x of t is modulating signal, x of t is equals to AM cos omega mt. C of t is a carrier signal, then C of t is equals to AC cos omega ct. Then the equation for AM wave will be S of t is equals to x of t plus AC into cos omega ct. Xc of t plus AC into cos omega t. Putting the values of x of t and c of t in the equation, we have S of t is equals to AM cos omega t cos omega ct plus AC cos omega ct. AC cos omega ct into 1 plus AM by AC cos omega ct. MA is equals to AM by AC. Then equation 15 can be modified as S of t is equals to AC cos omega c plus 1 into 1 plus MA cos omega CMT. To get the components of the spectrum of AM wave, equation 17 is further solved as S of t is equals to AC cos omega ct MA AC cos omega ct into cos omega mt. AC cos omega ct plus AC into MA by 2 cos omega ct minus cos omega mt. cos AX minus cos BX will be written as AC cos omega CT plus AC dot ME by 2 cos omega C plus omega M T plus cos omega C minus omega N into T AC cos omega T plus AC dot ME by 2 cos omega C plus omega M into T plus AC into ME by 2 cos omega C minus omega M T. That is statement the AC cos 2 pi FCT plus AC MA by 2 cos 2 pi FC plus FM into T. The AC into MA by 2 cos 2 pi. The amplitude versus frequency plot of a signal is known as frequency spectrum of a signal. The frequency spectrum plot of AM wave is shown in figure. To point to the horizontal axis represents the frequency and the vertical axis represents the amplitude. Voltage or current vertically, then frequency spectrum of AM signal in hertz. Voltage or current frequency FM will be at first. Signal frequency modulating signal, then FC minus FM lower side frequency carrier, underside frequency FC plus FM. Carrier is FC. Then the distance between the lower side frequency and the upper side frequency is the bandwidth of the amplitude modulated carrier wave. Frequency spectrum of AM signal. The modulating signal exists at FM on the frequency axis and the carrier signal is placed at the frequency FC. Two sidebands LSB and USB exist on either side of the carrier signal at the frequencies and respectively. The amplitude of the each sideband is equal to the MA into AC by 2. Therefore, the information is carried by two high frequency sidebands in amplitude modulation. The amount of space in the frequency spectrum required by the signal is called the bandwidth of the signal. The bandwidth of the AM signal is calculated as BW is equals to FC plus FM minus FC minus FM. BW is equals to 2FM. Power distribution in AM wave.
Thank you for watching. Do like, share and subscribe to my channel.